And welcome back to the Simpkins Physics Corner. I gotta check yourself before you wreck yourself. It's series circuits, but we gotta have a little intervention here because I saw the work that you turned in, and we need to talk about a few things. So let's go ahead and take a look at our series circuit organization tool. Now, some of you had an issue getting here. As I said in the last video, all you have to do is type in PHET DC circuit. That's it. You just gotta type that into Google. All right. There was a link on the Word document. Apparently that one didn't work and didn't get you there. But this is the one you're looking for, the FET, and you're going to go to the intro. All right, so let's talk a little about series circuits. Well, so far we know that charges will attract and repel, as if we're talking about positive and negative charges. And then we looked a little bit into this idea of voltage. So you know that a battery can be something like 9 volts. You're probably familiar with like the little black 9-volt battery. Voltage is the amount of push that the battery is going to give to these electrons. They call it electrical pressure sometimes. And here is a light bulb. And then we're going to go for a wire. We're going to go for another light bulb. We're going to go for a wire. And we're going to go for another light bulb. That's 3 light bulbs, in case you're counting. And we're going to go like this, all the way back to the beginning. Now, if we take a look at this circuit, this is called a series circuit. Think about like the World Series in baseball. They don't play game 5 and then game 2 and then game 3. That wouldn't even make any sense, right? The series circuit is called that because it goes in a series. It goes in order. It goes into the one bulb, out the one bulb, into bulb number 2, out of bulb number 2, into bulb number 3, out of bulb number 3. Now, look at this they call this a circuit or a loop. Look at this loop here. How many paths are there possible to take to get from one side of the battery to the other? Answer, only one. There's only one possible path that you can take to get from this side of the battery to that side of the battery. Sorry, I got super glare going on in my glasses, but actually it might turn out to be better anyway. Let's just keep them on so I can actually see what I'm doing. Now, if you look at your lab sheet, let's go to the 3, this one down here. I saw some very, let's say, interesting numbers for this one. When it comes to measured voltage for each of the bulbs, some of you had this like 10,000 number or 800 or something. Just click on the voltmeter. To measure voltage, you put black on one side, red on the other, and it says 9 volts. And look where I am. Look at what's between the black and the red. That's the battery. So that would go right here. The battery voltage is 9 volts. All right, let's try some other ones. Here's bulb number 3, as I called it earlier. And if it's negative, what do? Switch the red and the black. Bulb number 3 is going to be 3 volts. It's going to be that one. All right, let's go to the second bulb. Bulb number 2 here. That says 3 volts. And if you're catching a pattern, because all the bulbs are exactly the same, the other one will be 3 volts as well. And we can check that by using our little voltmeter on the simulator here. Boom, 3 volts. There it is. Okay, so the voltages are 3, 3, 3, and then of course they add up to the total of 9. So now let's take a look at the current at different points in this circuit. If we go here, you can notice here that all of these blue dots with a negative sign, the electrons is what that's representing. You notice that all the blue dots are going the same speed. Imagine like being in a traffic jam with somebody driving really slow at the front of this traffic jam. You all would have to go the same speed. And that's because there's only one path in a series. All the electrons have to flow the same rate. And the rate of flow of electrons is called current. So when we measure current with an ammeter, why is it called an ammeter if I'm measuring current? Because current is measured in amperes, or amps for short. And if I measure that current, you see at the battery it's 0.3 amps. So I'm going to come over to my spreadsheet. My battery current is 0.3 amps. And if I go back to the simulation, bulb number 3, 0.3. Bulb number 2, 0.3. Oh, right, we already said the current should be the same everywhere because all the electrons have to go the same speed. And so if I fill this in, 0.3 amps, go up for another one, 0.3 amps, go up for another one, 0.3 amps, okay? Now, check your data table. Go back to your document, look at it, check it out, and fix what you need to, all right? Because here's the things that I want you to notice. I'm not going to do the first one. You guys can figure that out. Oh, let me show you how to do the calculations real quick too. All right, so if you look at the top, V equals IR, right? That means R equals, if you do the algebra, V divided by I, okay? And that's just by doing the algebra rearranging that. So like for this one, V divided by I, voltage divided by current, would be 10. All right, some of you guys were putting 0 for resistance. If it was 0 resistance, everything would be on fire. Literally, I'm not joking. That's what would happen because no resistance would lead to a lot of heat being generated. And then we have 10 and 10, and that would add up to 20. If you do the math here, if you do 9 volts divided by 0.45 amps, you get 20. And what do you notice? You notice that the resistances of each individual bulb adds up to the total resistance of the entire circuit, or we call it the battery in this case. Let's look down here then. The resistance is still 10, and in fact, the simulation is set up so that all the bulbs have 10 ohms of resistance. Well, what happens if you take 3 bulbs, 10 each, and you put them all in a series? You got it, 30. All right. And so then for P, you just do P equals I times V. So you literally just multiply these two numbers together. So 3 times 0.3, let's see, 3 times 3 is 9, but it'd be 0.9 watts. All right. And you do the same thing all the way down because there's a lot of repeats because our bulbs are identical after all. And if we did that all the way down, and then we get to the bottom here, say P equals I times V. So again, we're multiplying these two together. 9 times 3 is 27. Swing the decimal, and we get 2.7 watts. So the reason I wanted to check you here is because at least half of you had all the wrong numbers in here. So I want you to go back and look at your worksheet and see what you did differently, and then go ahead and fix that. But what I want you to see are the big patterns. I want you to focus on what you wrote down here. So as you notice in this simulation, the bulbs get dimmer. Not dimmer, they get dimmer as you go. As you add more bulbs, they get dimmer. That's because, think about it this way. Think of it like it's getting warm out, right? So maybe you hook up your hose and your sprinkler. If you hook up a hose to one sprinkler, it'll probably shoot really high in the air. What if you hook up a hose to 2 sprinklers? They'll probably shoot not as high in the air. What if you hook up the hose to 3 sprinklers? They'll probably all kind of just be like barely trickling out, right? You can think of it kind of like that. Now, water is not a perfect analogy for electrical flow or current in this case, but what we can say is that the more bulbs that you have, the more light that is being poured out, kind of like the sprinkler shooting the water out, the dimmer those bulbs are going to be because they're all sharing this same amount of current, and the current actually gets weaker and weaker as the resistance goes higher and higher because there's more bulbs. All right, so for our summary here, what can you say about the bulb voltage and the battery voltage? Take a look. 3, 3, 3. What's that? Oh, they add up to 9. 4.5 and 4.5. Oh, they add up to 9. So here's what I want to say is they add up. And what we mean by that is the individual bulb voltages have to add up to the total voltage that's used in the circuit. What about bulb currents and battery currents? All right, this is a big idea for today. Same everywhere. The current at any point in a series circuit, doesn't matter if it's a battery, one of the bulbs, could be over here, could be over there. The current is the same everywhere. Again, because there's only one path to take. So if there's only one road, you can all only go the same speed, and there's no way to get around the slow people. What am I doing? Good Lord, give me that Word document, please. Thank you. All right. Last one, bulb resistances and the resistance of the entire circuit. Well, if we take a look at our data table, 10 plus 10 plus 10 is 30. 10 plus 10 is 20. And this one would just be 10 because the total, it's only one bulb. And so what we see here is that the resistances add up as well. Okay, so those are the big ideas for series circuit. All right, the more bulbs you have, the dimmer everything gets. The voltages have to add up, and the currents are the same everywhere. All right, and the resistances add up as well. So let's apply that. Some of you guys took a crack at this, what we call a VIRP table, and I'll help you out with this a little bit. This is a table for 3 light bulbs, and what we're looking at here is calculating the missing pieces. So let's take a look. We got V and I here. Well, this is R, and if we look at our data table from the lab that we just completed, R equals V divided by I. So what would that be equal to here? Well, V divided by I would be 10 volts divided by 2 amps, which would be 5. So 5 ohms would be our resistance for that one. Okay. Now power P equals IV. That's from, you can look at the table on the previous page again. I times V would be current is I times V is volts, and that would be 20 watts. Excuse me. All right, now here's the big idea. In series, there's only one path, and so something is the same everywhere. Do you remember what's the same everywhere in series? Oh, current is the same everywhere in series because the rate of flow of the charge has to be the same everywhere since there's only one path. There's only one street. There's only one road. Everybody's got to go the same speed. All the electrons have to be moving at the same rate of 2 amperes. All right, so 2 amps for all of them. And now you can see the puzzle starts to be unlocked a little bit, right? Because here we have P and I, and we know that P equals IV. Oh, so that means that V equals P divided by I, which means if I want to solve for voltage, I just do 10 divided by 2, or 5 volts. Sweet. So if you missed that, pause the video, go back a couple seconds, and listen to what I just said again. You should slow down if you need to. For R, we're going to look at that R equals V divided by I. So V, volts, divided by I, amps. That's going to be 2.5 ohms. Cool, we move down the table. This one, we don't know anything but the amps, so I'm going to skip that for now. And here we have V, and we know that voltage is equal to current times resistance. So if I look at these numbers, 2 times 10 would be 20 volts. And then, of course, power is IV, so that's going to be 2 times 20. That's going to be 40 watts. All right, so we're almost there. We're almost there. Here's where we have to crack into the last part though. Notice how many volts we have. We have 10 volts, we have 5 volts, and we have 20 volts. Now, let's go back and look at our rule here. Our rule said that in series, the voltages have to add up to the battery voltage. Well, our total voltage down here is 20, and I have 10 and 5 so far. How many more volts am I going to need at that bulb 3? If you're thinking 5 volts, you're on the right track. Why? Because 10 plus 5 plus 5 equals 20. The bulbs in a series have to add up in their voltages to the total voltage. And then we do the same calculations over here. R equals V divided by I. So 5 over 2 is going to be 2.5. And it's resistance, so that's going to be ohms. And no surprise here that power would be 10 as well. And it just so happens that power adds up also. All right, so I hope that you guys found this video helpful for analyzing series circuits. I'm going to post a follow-up assignment today, and what I want you guys to do is try out just one of these VIRP tables. It's a very short assignment. I want you to go back and look at these rules right here. I want you to try out one more VIRP table, which is where you're solving for the missing pieces. And please, send me a message if you don't know what's going on. I see that a lot of you are working together, and that's great, but when I get half of the assignments that have all the same answers that are all wrong, I wish somebody would have reached out and asked a question since you had 2 days to do that assignment. So please be sure to do that this time, but just submit those updated VIRP tables for the next series circuit, and let me know if you need anything. If you need me, I will be here waiting for you in the Simpkins Physics Corner.